took a break, maybe you got to take a break also. During this session, what I'd like to do is do some practice problems to cement some of these ideas that I just shared with you. Before we get into the practice problems, I want to make you aware that there's this booklet that actually has, this is what you're allowed to take into the exam. There is a chemistry chapter in it. It's just 2 pages. It gives some simple definitions of words. It also has a periodic table in it, and some of these organic chemicals are named as well. So you may want to take a look at that as you prepare for the exam. Also, you may want to purchase something that looks like this, the EIT Review Manual. It has about 3 chapters related to chemistry with lots of worked out solutions to practice problems. So there's a lot of material out there to help you learn your chemistry. I happen to have some other practice problems that I've gathered over the years, and so we're going to go through these rather quickly because you have them in your notes, and I'm just going to sort of skim through them and help you see how we do this various things. Okay, the first question says, which statement is correct? Solutions may be homogeneous or heterogeneous. That's incorrect. Solutions are by definition homogeneous. Matter may be homogeneous or heterogeneous. That's true. Solids you could have solids and vapors in equilibrium, so that would be heterogeneous. Both elements and compounds are composed of atoms, which is true. All substances contain atoms, yes. And substances are always homogeneous. That's what a definition of a substance is. Okay, which of the following statements is not correct? An element may be separated into atoms. An element may be a gas, a liquid, or a solid. A compound can be separated into its elements by chemical means. An element is always heterogeneous. A compound may be a gas, a liquid, or a solid. Well, this is a not correct statement. An element can be heterogeneous, but it could also be homogeneous. In relation to a proton, the electron is much lighter and of opposite charge. A negative ion of a certain element can be formed by adding an electron to that atom of that element. That's pretty straightforward. Here's a discussion about metals, which we had remember everything to the left of that line is a metal, everything to the right is a non-metal. Metallic conduction means there's passage of electrons from one atom of metal to another. Let's see. Which of the following statements is true? Within a period of elements in the periodic table, the noble gas has the highest ionization potential. To understand this, there's actually tables of ionization potentials listed in chemistry books. It's an idea that's closely related to electronegativity. My personal feeling is you're probably not going to see a question like that on the exam. That's just a little bit too chemistry-oriented for engineers. This next question is, which has the largest atomic radius? Well, you need the periodic table in order to see this. Here's lithium. Then we go to sodium, so it should be getting a little bit bigger because we're adding more electrons to it. Beryllium. Here, we're adding more electrons to it, so that should get bigger. Magnesium is over here, but take a look at phosphorus. It's way over here at the right, has lots of electrons, it's way to the right, so that's going to be the biggest atomic radius. In the series, boron, aluminum, gallium, indium. So let's take a look at getting the periodic table. Here we have boron, aluminum, boron, aluminum, gallium, indium. What we're doing is going down the periodic table. So notice that what's happening is that here we were to the right of this heavy line, and then we're moving further away from the heavy line, so the metallic character is increasing as we move down this. The next question is, which of the following lists contain only nonmetals? We have carbon, sulfur, and fluorine all to the right of the heavy line, so those are all nonmetals. Let's see, in an element, the atomic number is equal to the number of protons in the atom. Here we have a question regarding aluminum. What's the ground state? That is, we haven't pumped it up with any energy, so the question is, where are the electrons? Okay, again, here's the periodic table. With aluminum, we've got, you can imagine this helium being located here, so we're filling up the S. So we've got the 1s filled up, the 2s, the 2p is filled, 3s, and then we've got 3 electrons in the 3p. So that's why I answered E is correct there. Now these next couple questions are just unlikely. They're too detailed, and I doubt that they would give those questions to engineers on the exam, so we're just going to skip those. At least this 412. Now this next one is a possibility. Here we have group 6, which is located right here, group 6. What that indicates is that we are busy working on the p electrons, and that there are 4 electrons in the p orbital. So that's what that means. Okay, this next question is, by considering electron configurations, what's the most similar to strontium, atomic SR? Right, so here's a periodic table. Let's see if I can find it. Here it is over here. There's strontium, and notice that barium is right underneath it. So remember that things in a column have similar properties, so you'd expect barium to be very similar to strontium. These next 3 questions are unlikely. They're just too detailed. I don't think you would see those. How many electrons does a phosphorus atom have in its valence p orbitals? This is the phosphorus again. Remember, all these are p orbitals, and so it has 1, 2, 3 in the p orbitals. Here we have an unknown element, Q, has a mass of 31, and the nucleus contains 15 protons. That happens to correspond to phosphorus again, and you can just see right there the periodic table. It has 15 protons in it, so that's pretty straightforward. This next question was, you have an ion of an unknown element. It has an atomic number of 15. It has 18 electrons. What is it? Well, again, phosphorus has an atomic number of 15. That is, it has 15 protons. And since it's got 18 electrons, it has 3 extra ones, which will give it a -3 charge. So that's what that comes from right there. Okay. Regarding molecules, regarding ionic and covalent bonds, what's true? In a covalent bond, each atom is bonded to only 2 other atoms. Well, it could be more. Methane is a good example. An ionic bond is an electrostatic interaction localized between 2 definite ions of identical electric charge. That's not necessarily true. A covalent bond occurs when electrons are completely transferred from one atom to another. Is false. It would be made true if we replace the word covalent with ionic. When a covalent bond forms between 2 atoms with different electronegativities, the bond is always polar. That's true, that the more electronegative element will take electrons from the other one. So D is the correct answer there. Which of the following is classified as an alkane? This gets into fine points of organic chemistry. You can see that the alkane ends in ane, methane, propane, ethane. So that would be the trick there. The ene would be alkenes. And the alcohol would be, ethanol would be an alcohol. Okay, which of the following bonds is most covalent? What we're looking for is which ones have the most similar electronegativities. And if we pull out our electronegativity chart again, if we look at aluminum and phosphorus, they differ by only 0.6, and all the other ones differ by more. So it's just a matter of comparing the electronegativities and choosing the ones that are most similar, which means, therefore, that they are the most covalent type bond. Okay. The sum of the oxidation states of all the atoms in a neutral molecule must be 0. And this is a topic I really haven't spent any time on, but I'll give you a quick primer on it. The oxidation state these are the rules. You have a covalent bond, but what you do is, by the formalism of the oxidation state, you put all the electrons onto the most electronegative charge. So, for example, if I had methane again, recall that carbon is more electronegative than hydrogen. So remember those 8 electrons that are around it. The extra 4 are all going to be put onto carbon. So the formalism is that carbon would have a negative 4 charge because it's a more electronegative, and the hydrogen would have a +1 charge because it couldn't hold on to its electrons. So that's the formalism. Now in this case, methane, we have a neutral molecule. We have 4 plus 1s, and we have 1 minus 4, so the sum of the oxidation states has to be 0. Here's another question related to oxidation state. The oxidation state of an element bonded only to itself, for example, hydrogen, also is 0. They each have an identical electronegativity. So rule 2 is that if you have identical elements, they are shared equally, and you do not assign charge to it. Let's take a look at another example. Here we have sulfite ion, which is SO3, and it's got a -2 charge. So this is an example of a radical. And so the question is, what is the oxidation state of the sulfur? Well, oxygen always has a -2 oxidation state. It grabs 2 extra electrons to get 8 in its outer orbital, so you always know that you can put -2 for the oxygen. And of course, there's 3 of those, and the sum total of this has to be equal to -2, so our unknown x, that is, what is the oxidation state of sulfur, 4 solves that equation. A mole is an Avogadro's mole of number of anything. I sure would love to have a mole of dollar bills. I'd be a very wealthy man. In fact, I'd be much richer than Bill Gates if I had a mole of dollar bills. Even I'd take a mole of pennies. Which statement is incorrect? And Avogadro's number equals the number of atoms in 1 mole of nitrogen molecules. It's really a half mole of nitrogen molecules. The nitrogen molecule is dinitrogen. Okay, here's an example using molecular weights. We have an empty Coke can that weighs 50 grams. It's made out of aluminum. How many moles are in this Coke can? Well, the molecular or atomic weight of aluminum is 27. Meaning there's 27 grams in a mole. I've got 50 grams. Cancel out the units. So there's 1.85 moles of aluminum in a can. And think about how many think of Avogadro's number. There's a lot of aluminum atoms in that aluminum can. Here we have 27 grams of oxygen difluoride, and how many molecules? So here we've got atomic weight of oxygen is 16, fluorine is 19. Here's Avogadro's number, and so what we've got is what we have to do is calculate the atomic weight. So we've got 16 for the oxygen, 19 for the fluorine. We've got 2 of those, and so we get 56. And so there's 27 grams. This will get us how many moles there are. This is how many species in a mole. And so there's about 3 times 10 to the 23 of those species in there. It's interesting. You make a rule and then you correct yourself. If you have the species OF2, the oxidation state of oxygen would be not -2 in that case. Fluorine, being more electronegative, would steal the electrons from it. So I stand corrected. In that particular case, oxygen would be +2 and fluorine would be -1. Let's move on. How many grams are there in 0.01 moles of sodium sulfate? So what we have to do is calculate the molecular weight of sodium sulfate. Sodium sulfur, oxygen, 142, 0.01 moles of it. There's the molecular weight. Cancel out the moles, and so there's 1.42 grams right there. What's the volume at standard temperature and pressure? Remember, standard temperature is 0 degrees Celsius or 273.15 Kelvin, and pressure, standard pressure is 1 atmosphere. And we've got 16 grams of gaseous sulfur dioxide, so what's the volume? Okay, well, the molecular weight of SO2, sulfur is 32, and oxygen is 16, so the molecular weight is 64. So we've got 16 grams, and there's 64 grams in a mole, and at STP, standard temperature and pressure, there's 22.4 liters, so that means that in a mole, so that means we have 5.6 liters. And you can just cancel out your units and make sure you get the right answer. What's the percentage of weight of aluminum in alumina? Alumina is the natural ore from which aluminum is mined. Aluminum is a molecular weight or atomic weight of 27, oxygen is 16. So the molecular weight of alumina is 2 aluminums and 3 oxygens, or 102. And so we've got 2 of these aluminum species that each weighs 27, and the entire species weighs 102, which comes out to be 53%. Okay, we've got some unknown compound that has sulfur and chlorine in it. It's 47.5% sulfur, and the molecular weight is 135. What is its formula? Okay, so what I did is I simply went through and tried a bunch of them. When I looked at this sulfur dichloride, there's 1 sulfur, and then the total weight is the sulfur with 32 and the 2 chlorines. It was only 31% sulfur. When I went to the next one, there's the sulfur in the numerator, and then there's the sulfur plus the chlorine in the denominator, which would be the total weight. It's 47% sulfur, and that answers the question, so why waste the time looking at the others? Here we have an unknown organic compound. It's found to have 34.6% carbon, 3.8% hydrogen, 61.5% oxygen. What would that be? All right, so again, I just stepped through taking a look. So first thing to do is calculate the molecular weight. Methanol has 1 carbon, 4 hydrogens, and 1 oxygen, so it weighs 32. Carbon weighs 12 out of the 32, so it's 37.5% carbon. That doesn't answer the question. Next we do oxalic acid. It has a total weight of 90. There's 2 carbons in it, and so it's 26.7% carbon. We go through that and we get a hit on malonic acid. It's got total molecular weight of 104, and there's 3 carbons in it, and it comes out to be 34.6%. Okay, here we have an equilibrium reaction. This compound breaking into nitrogen oxide and chlorine gas. And so what we're trying to do is come up with the equilibrium expression for this. Recall that it's always products divided by reactants. So the products would be these species divided by that species. And then the other thing to be aware of is that we have the right exponent. And if we have 2 of these, so there's that 2 right there corresponds to that 2. We have 2 of those, so that 2 is for that. And we have 1 of these, so that 1 is for that. So that the question here is, can you form an equilibrium expression given the stoichiometry? Okay, here we have another case where we have a solid reaction. This case, barium oxide reacting with carbon dioxide. Here's the equation. Come up with equilibrium expression. Recall that I said that if you have solids, simply ignore them in the equilibrium expression. So here's the product, barium carbonate. In the numerator, we have the reactants in the denominator, barium oxide, carbon dioxide. Barium carbonate is a solid, barium oxide is a solid. Simply take those out, and so the equilibrium expression would be 1 over the carbon dioxide concentration. Here we've got excess oxygen reacting with methane to form 14 grams of carbon monoxide. Here's the reaction, methane and oxygen going to carbon monoxide and water. How many moles of methane will be consumed? Okay, so what we need to do is calculate the molecular weight of carbon monoxide. Carbon weighs 12, oxygen weighs 16, so it weighs 28. It says we made 14 grams of carbon monoxide, so we start with our 14 grams. Here's the molecular weight, so the grams of carbon monoxide cancel. So now we have moles of carbon monoxide. Then what we do is we look at the stoichiometry, and the stoichiometry says for every 2 moles of carbon monoxide that react, there are 2 moles of methane that react. So we simply set up this ratio. The moles of carbon monoxide cancel. We're left with moles of methane. So the answer is a half a mole of methane would react in order to make 14 grams of carbon monoxide. Here we have an equation. The question is, what coefficient is required for this species in order to balance it? And this can be done by the by guess and by golly method, really. We've got nitrate, we've got 2 nitrates, and then we've got 2 of those lead nitrates. So we say I've got 2 nitrogens times 2, so there's a total of 4 nitrogens on the left. I don't see nitrogen anywhere else, so that means I have to have 4 of these in order to get a balance. What coefficient is required to balance this reaction for the water? So that's the question. In this case, oxygen is unique to water on the left-hand side, so we can just look at the oxygens on the right-hand side. So we see we've got 2 oxygens in that hydroxide ion, and there's 3 of them. So we have 3 times 2, so there's 6 oxygens on the right, and we better have 6 oxygens on the left. So the coefficient here has to be 6. Here we have a reaction with magnesium and nitrogen, making magnesium nitride. And the question is, what's happening to the oxidation states? Okay, remember when things are elemental, we say that they have an oxidation state of 0. And we take a look at nitrogen. Here's nitrogen on the periodic table. It would like to gain 3 electrons in order to become a stable shell. So the nitrogen has a formal charge of -3, because it's going to pick up the extra electrons, and the magnesium is going to lose 2 electrons. So what you can do is take a look at this. We've got nitrogen going from 0 to -3. That means it gained electrons, and therefore it is reduced. Here we've got a reaction between aluminum hydrochloric acid. According to this equation, it says 1 mole of... It's interesting how they've got it written. The stoichiometry says that 2 moles of aluminum chloride are formed from 2 moles of aluminum, or you could simply simplify that and say 1 mole of aluminum gives 1 mole of aluminum chloride. It's 2 to 2 or 1 to 1. It's a ratio. When crystals of sodium sulfate are dissolved in water, the resulting solution feels warm. What that means is that heat was given off by that reaction. That is, as the sodium sulfate dissolved in water, there was a reaction of type, of A type. That is an exothermic reaction. So if it's exothermic, that means it wants to give off heat, and you can help it give off heat by doing the reaction at a low temperature. So if you want to increase the solubility of sodium sulfate, drop the temperature. That will make this exothermic reaction more favorable. Okay, here's a statement. Which of the following statements is false? An exothermic reaction always goes faster than an endothermic reaction. It's kind of attractive. It looks like it might be true, but you're mixing up kinetics and thermodynamics. Endothermic and exothermic relates to the energetics of the reaction, which is a concept of thermo. That says faster is a concept from kinetics. And so the two are really different disciplines, although they're connected. That's 2 different ideas. All the other statements are true. Take a look at this last one on this page. Which of the following reactions would increase in volume of the container? Which of the equations, if you increase the container volume, would help the equilibrium? So what we're saying is that we want to look for a reaction where there's an increase in number of moles, that the pressure would go down. So if we take a look at this reaction, we've got actually 7 species. There's an error here. 7 species going to 4. So that's a decrease in moles, so that's not going to be favored by increasing the volume or dropping the pressure. Here we have a solid, and so that's essentially removed from the reaction. So we have one gaseous species going to one gaseous species, so the pressure or the volume doesn't do anything with that. Here we have two gases going to a liquid. By dropping or by increasing the pressure, we can make moles go away and favor the reaction, so that's not what we want. Here we have 2 moles going to 2 moles. So the answer that's correct is right here. We have one species going to 2. We're increasing the number of moles, and that says that's favored if you increase the volume or decrease the pressure. Okay, here we've got a statement: the rates of most chemical reactions increase as the temperature increases, primarily because at higher temperatures there are more collisions of sufficient energy. So as you increase the temperature, the molecules are more energetic. A greater fraction of them have enough energy to react, and that's why increasing the temperature increases the rate of the reaction. Here we have electrolysis. Here's the anode. I'm using sodium chloride as an example. The negative species is attracted to the anode, which is of course positive, and so the sodium is attracted to the cathode. And so to answer the question, the anions migrate to the anode, cations migrate to the other electrode, which is a cathode. The statement that equal volumes of all gases under the same conditions of temperature and pressure have the same number of molecules is known as Avogadro's law. Okay, here we have arsenic oxide reacting with carbon to form carbon monoxide and arsenic. The molecular weight of this is 198, and the atomic weight of this is 150. And so if I were to have 1 gram mole of this react, that is to say 198 grams, I would form 150 grams of this product, according to the stoichiometry. Here we have ethane burning. This is the balanced reaction. What volume of carbon dioxide measured at STP is formed for each gram mole of methane burned? Well, if you look at the stoichiometry, there's 4 moles of carbon dioxide per 2 moles of methane or of ethane. According to STP, there's 22.4 liters per gram mole of anything, in this case CO2. And so if we burned 1 gram mole of methane, we'd end up with 2 gram moles of carbon dioxide, which would occupy 44.8 liters. The tendency for a reaction to occur is greatest for those chemical reactions in which a large amount of heat is involved. This introduces a concept that I haven't talked about yet. What really drives reactions is what's called the Gibbs free energy, which is defined to be the change in enthalpy plus the temperature times the change in entropy. If you really want to drive a reaction by making the enthalpy change negative, that is to say an exothermic reaction, that can very strongly make the Gibbs free energy negative. Now in some cases we could overcome that through entropy considerations, but they made a point of saying a large amount, so it's unlikely entropy would ever be able to overcome that. So if you have a large amount of heat given off that is a very strongly negative enthalpy, that'll make the Gibbs free energy change also negative, and a negative delta G is what makes the reaction go. So that's a little bit of thermo there. The valence or oxidation state of manganese and potassium permanganate is, well, we've got potassium, magnesium, and oxygen. Remember I said oxygen has a -2 under most normal circumstances. If you take a look at potassium, it's right here. It would very much like to shed an electron so that it can have 8 electrons in its outer valence orbitals. So potassium takes on a +1 charge. Of course, there's no net charge on this species, so the total has to be 0. So manganese has to have a +7 in order for that equation to work out. Here we've got element number 37, rubidium. It's found in group 1A, which is right here. There's the rubidium. we'd expect to have all the following properties except forming a charge of +2. See, rubidium is right here. By shedding its extra electron, it can sort of look like a krypton, which is right there. So it sure would like to shed 1 electron, not 2, which is why statement C is wrong. Which of the following elements would not be expected to form a positive charge? Sulfur is located here on the periodic table. It's just too far to the right. It would like to pick up extra electrons in order to complete the outer shell. It'd have to shed an awful lot of electrons. It'd have to shed 6 electrons, and that's pretty hard to do. Okay, here we have an oddly written equation. We've got species A going to B subtracting heat. The way I would prefer to write that is put the heat on the other side, so heat plus A goes to B. You can think of these things as just ordinary mathematical equations, put them on either side as you care to. So since we have to add heat to make this thing go, that means it's an endothermic reaction. And then we see that there's a decrease in moles. So what that says, endothermic reactions are favored by high temperature, and if we increase the pressure, we'll force it to the right, because it can get out of the way of that high pressure by shrinking and forming product. Here we have acetine. It's element number 85, group 7A, which means it's right here. There it is. It's in the same column as chlorine and iodine, so which would not be characteristic of it. Here they have it reacting 2 hydrogens reacting with it. It should really just be 1 hydrogen, like hydrochloric acid just has 1 hydrogen, not 2. Okay, which of the following elements is least likely to form a negative ion? Here we've got all these. Take a look at chlorine. It's right there. Picking up an extra electron will make it have 8 electrons. We've got sulfur. Picking up 2 will help it get the 8 it wants. Oxygen we want to pick up 2. But here we have strontium, which is way over here. Let's see where. Here it is. Strontium number 38. It would rather shed its electrons. It would rather shed 2 electrons rather than pick up electrons. Let's see. Here we're going to electrolyze an aqueous solution of potassium bromide. What species migrates towards the positive electrode, that is the anode? Well, the bromine has a negative charge, so it's going to be attracted there. In order to determine the number of moles of nitrogen in 3.7 liters at STP, you'd use Avogadro's law. Here's another question on the oxidation number of potassium chlorate. We've got oxygen again with -2, potassium with +1. So the question is, what's the charge on chlorine? There's no net charge on the species, so that's equal to 0. So we'll find that a +7 charge will satisfy this. So in essence, we're saying that oxygen is taking electrons from the chlorine to give it the +7 charge. And let's make sure that that's reasonable. Yes, if you take a look at the electronegativity, you see that chlorine is 3.0 and oxygen is 3.5. So what's happening is the oxygens are going on to the oxygen, so this formalism, chlorine is in essence lost 7 electrons. Didn't really lose 7, that's just where you're assigning them. Here, the fact that there are fewer collisions between molecules of gases at lower temperature means a smaller rate constant. Which of the following would not increase the amount of product in the following reaction? Here we've got an equilibrium, and hydrochloric acid is the catalyst. So at equilibrium, adding more catalyst does nothing to change the ratio. It will increase the rate at which this reaction comes to equilibrium, but it does not affect the equilibrium. Here we have an endothermic reaction at equilibrium. So the key word here is endothermic. Which of the following would shift the equilibrium to the right? Okay, so endothermic meaning we're going to add heat. Since we want to add heat, that means it's easier to add heat at a high temperature, so that'll help us out. And I see here that we have constant moles. We have 2 here, 2 here, 2 here, 2 here, so pressure or volume doesn't really do anything for us one way or the other. Oxidation of propene with potassium permanganate proceeds as follows. It's not a balanced reaction. Here's the propene. Here's the potassium permanganate. Just to reinforce our ideas, potassium permanganate is an oxidizing agent. It will cause the propene to be burned, in a sense. You can see here on the right we introduced some oxygen into it, so this propene has become more oxidized because of the oxidizing agent. If we were to use other words, we could say that the propene is a reducing agent that caused the potassium permanganate to become reduced, meaning we helped give it electrons to that oxygen. So hopefully that'll help you reinforce those complicated notions. Okay, so we have in the balance equation, how many liters of carbon dioxide would be formed from 1 mole of propene? So what we'll have to do is try to balance this equation. Easiest to balance it based on carbons. You see there are 3 carbons here, 2 carbons, and 1 carbon. So using the by guess and by golly method, if I have one of those will make it balanced. So that is rather quickly balanced. So that says there's 1 mole of CO2 per mole of propene, and at standard state you get 22.4 liters per mole, so we would have 22.4 liters of carbon dioxide resulting from this reaction. Here we have iron reacting with copper sulfate. Here's the stoichiometry. It's an unbalanced reaction, but what we can do is balance it. We have 2 irons on this side, so we need 2 on that side to balance it. We have 3 sulfates on this side, so we'll need 3 sulfates on that side to balance it, and that means we'll end up with 3 coppers. So if we have 1 gram mole of iron, this says that there are 3 gram moles, gram atoms of copper per 2 of iron. That's what the stoichiometry says. And then the atomic weight is 63.5 grams of copper per gram atom of copper. So we go through the math, cancel out units, and we'll end up with 95 as grams as the correct answer. Okay, that completes the review of both the theory and the practice. Good luck on the EIT exam.